Hello guys. Today I'm bringing you a couple more of examples. We're gonna start this example, and this example deals with moment in 3D. It says the pipe assembly is subject to a 80 Newton force and determine the moment of this force about the point A. There's a similar problem also that asks you to determine the force about point B, but we're gonna do it about point A. So basically, because this is a 3D problem, you can focus it in several ways, and you can try to start studying what effect this force is doing regarding rotation about this axis, about this axis, or about this axis. But that's, for the beginner, that's complicated, and not for the not so beginner also is complicated. So what we are going to do, and what I advise you to do, is apply the formula for moment as a vector. Moment of the force F with respect to the point A is going to be equal to the cross product between the arm from the point A to the point where the force is applied times the force. So in other words, this arm, or moment arm, is the distance, or is the vector, from the point where we want to calculate the moment up to the point, any point on the line of action of the force. So from this point to this point. This is going to be my arm. And notice, and this is really important, and I repeat it several times for this reason, is from the point I want to calculate the moment to the point where the force is applied, or any other point along the line of action of the force. So basically, if we know this, our problem just is calculate R, or determine R and determine F. Let's start with R. RAC is the arm, once again, of the moment, and is the distance between from the point where I want to calculate the moment to the point where the force is applied. Well, let's check this out. In X, from this, you can calculate coordinates if you want to, but you can also run the vector. What I have here is in X, which is this axis, I have from this point A, 300 plus 250 is 550 millimeters. In I, Y is this distance, so basically everything is, this part is parallel to this 400, so that distance is going to be 400 J. And in K is the distance from this plane downwards, 200. If it's downward, it's going to be negative 200. And this is also millimeters, and this is also millimeters, so everything is in millimeters. Or if I want to express this in meters, then this is only one arrow here, not two. AC is going to be equal to 0.55 in I plus 0.4 J minus 0.2 K, and this is going to be in meters. Remember that 1 meter is equivalent to 1,000 millimeters. So we have our vector arm, and the next thing that we have to do is express the force F as a vector also. How do you express the force F as a vector? Well, the force F as a vector is going to be equal to the magnitude of the force F multiplied by a unit vector in the direction of F, or it could be also calculated using projection angles, or cosine director angles, or any other way that you have to. In our particular case, you are given basically the angles here, so you can project the angle, the vector. What is the first thing that we have to do? Well, the easiest coordinate to calculate is this one. The first one, this one. And this is going to be FZ. And why is the easiest one? Because you can see that this line here is over the plane, the XY plane, and this is FC directly. And if this angle is 30 degrees here, this angle here is going to be 90 degrees in this part. So my Z component goes in negative direction, of course, and it's going to be negative 80 times sine of 30 degrees, which means that this is going to be negative 40k, because sine of 30 degrees is 0.5. And remember also, this is going to be given in the force units, which are Newton. So I have the first component. Now for the X and Y component, this is going to be my Y component for the force, and this is going to be my X component of the force. But in order for calculating those two, the first thing that I have to do is calculate this projection here. And that projection, you can call it whatever way you want, but that projection is basically the projection of the force over the plane XY. You can call it F prime if you want to. A bunch of books calculate that and call it F prime. But anyway, that the way you calculate it or the way you name it is not what matters. What matters is that this is adjacent to this 30 degrees. So that value is going to be basically 80 multiplied by cosine 30 degrees. Now, if I want to calculate my X component, which is this one, this is the angle that I have to use, 40 degrees. So basically, my X component goes and points in the X positive direction of the axis, and it's going to be equal to the projection that I call XY multiplied by, once again, I'm talking about this one here, so it's the opposite of this 40 degrees. It's going to be sine 40 degrees. Putting this in here, that's going to be equal to 80 cosine 30 degrees multiplied by sine 40 degrees. Or Fx is going to be equal to 44.53 I, and this is Newton. For Fy, which is this other component in this direction, what I'm going to have is basically the projection that I call xy, this projection, multiplied by cosine of 40 degrees. Or in other words, I can get this and plug it into here also, and then we are getting f times cosine 30 degrees multiplied by cosine 40 degrees. Or Fy equal 53.07J, and this is also Newton. At the end, we can say that our force F as a vector is no other thing that Fx 44.53 in I plus 53.07 in J plus negative 40K, and this is Newton. Now I have F, I already calculated, and I have R. I have to do the cross product RF. What is the cross product RF? Well, let me put here the cross product RF. This is I, JK. Remember, it is extremely important for you to remember, once again, I know it's a redundancy, remember, but maybe if I say that remember, you will remember that first goes R and then goes Z. This is going to be 0.55, 0.4, negative 0.2, and then Fz is 44.07 0.53 in I, 53.07 in J, and negative 40 in K. When we solve this determinant, it's going to be I that multiplies 0.4 times negative 40 minus 53.07 times negative 0.2 minus J that multiplies 0.55 times negative 40, this times this, minus this times this, so minus 44.53 times negative 0.2 plus K that multiplies 0.55 times 53.07 minus 0.4 times 44.53. And then this is going to be our moment of the force F with respect to the point A. Now I'm putting double arrow here because that's a way of differentiating moment vector from any regular force vector. And when I do this multiplication, this is going to be equal to negative 5.39 I plus 13.1 J plus 11.4 K. That's basically what the problem is asking us to calculate. This is a simple problem that shows you basically the whole procedure. First thing first. First thing, moment equal R cross F, not F cross R, R cross F. Calculate R, which is the point, the distance from, or the vector from the point that I want to calculate the moment to the point where the force is applied, or any point within the line of action of the force. Express that R as a vector, express F as a vector. You have several ways of doing it. In this particular example, it was easier to use the projection angles here and here. You have the Z component, and then this one goes over the XY plane. This one is like this, goes over the XY plane, and then goes to one side or to the other side. This is cosine 30, and then this is cosine 40 for the Y, cosine 30, sine 40 for the X, and simply sine 30 for the Z, and do the cross product R cross F and get the moment. That's the first problem that I have for you. Now the second problem. Second problem, I brought this, which is basically moment with respect to an axis. And there are several ways of doing this problem also. I'm going to try to at least mention the different ways, or some of the different ways that you can do this problem. The problem says, if the tension in the cable is F equal 140 pounds, so I know this F is 140 pounds, determine the magnitude of the moment produced by this force about the hinge axis CD. So basically, it's not the moment about the point now, it's a moment about an axis. What axis? This axis here. That axis. So that means that we have to calculate the rotation that that force is producing or is causing to this element around that axis. How do we do that? Well, once again, there are several ways of doing it. We can calculate the moment of the force F with respect to any point that lies in that line of action. I'm going to calculate the moment of the force F with respect to the point C. And after that, you do the dot multiplication of the unit vector of the axis that you want to calculate the moment component. So basically, the moment of the force F, or the magnitude, no, the moment, not the magnitude, the moment of the force F with respect to the axis CD is equal to the moment of the force F with respect to any point in the line of over the axis, dot multiplied by the unit vector of the axis. This is the first way of doing it. You could also say, oh, because it's any point, then I'm going to say that this has to be equal also to the moment of the force F, but now with respect to the point D, because the point D is also in the axis, and dot multiply that by the unit vector of the axis. Yes, you can do that also. As a matter of fact, I'm going to do this. I want you to do the other one and prove it. And also, you can do the triple scalar product. Instead of doing this, you can do what is called the triple scalar product. What method are you using? Depends on convenience, depends what the problem is asking you to do, depends if the problem is only asking you for the final moment, because sometimes the problem tells you calculate the moment with respect to the point C and then calculate the moment of the force over the axis. Well, if that's the way, of course it's obvious that you have to use first calculate the moment over the force C, which is the first step, and then dot multiply. But if the result is the final result, I will go through triple scalar product. Now, point C or point D, and I'm going to go beyond that also. We can do something else, but I'm going to do it in the next part. Let's start from the basics, and let's say that I'm going to use the first approach. I'm going to calculate the moment of the force with respect to the point C first, and then dot multiply by the axis. First, I need to know, in order to calculate that, what is my arm. And the arm is, once again, from the point where I want to calculate the moment, which is the point C, to the point where the force is applied, or any point in the line of actions, here. Okay? So let's do that. How I'm going to do that? Well, this is my vector here. My vector CA, because the moment of the force with respect to the point C, basically, what I'm saying is going to be F cross CA. So then I have to know how much is CA. CA is 6 in I, and nothing else because it's over the x-axis. So this is going to be my arm, 6I. And remember, the units from time to time, it's good to copy them, doesn't fit. Now the next thing that I know is the force, and the force I needed in Cartesian formulation, in Cartesian notation. So I don't have the force as a Cartesian vector, but I can say that is the magnitude of the force, which I know the problem is giving us, multiplied by a unit vector in the direction of the force, which is no other thing than AB, in the direction of the axis AB. We can do that. Magnitude 140. So let's start with the vector AB. If I want to calculate the vector AB is going to be from here to here. That means that vector is going to be negative 6 here, negative 6 in I. Why negative? Because it's going back. Then I'm going to go up in K, 12. And then I have to go in this direction in I, so it's 4 in J, I mean Y, J. Or you can calculate these coordinates and subtract B minus A if you want to. The coordinates for the point B are 0 in X, 4 in Y, 12 in K, and the coordinates for this point are 6, 0, 0. Then you can subtract this point minus this point, and you have 0 minus 6, negative 6, 4 minus 0, 4, 12 minus 0, 12. Whatever way you want to do it is okay. The way that you understand is the best. So now, I don't do anything with this one because what I need is the unit vector. But the unit vector is going to be exactly the same thing divided by the magnitude, which is 6x squared plus 4 squared plus 12 squared. And then if I want to calculate my force, it's going to be the magnitude of the force, which is 140, multiplied by the unit vector, (12k), divided by the square root of this, and the square root of this is 14. So basically this is going to be 10 times 6 is going to be negative 60i plus 40j plus 12k, 120, okay, and that's my force F. Once I have that force F and I have my arm here, I calculate the moment of the force F with respect to the point C, and that is IJK. Remember first R, so it's 6, 0, 0. Then F, negative 60, 40, 120. And that is going to be basically I, that multiplies 0 times 0, 0 times 0 is 0, minus J, that multiplies minus J, that multiplies 6 times 120, this times this minus 0, plus K, that multiplies 6 times 40 minus 0. So my moment of the force F with respect to the point C is going to be negative 720J plus 240K. And the unit for this are pounds per foot. This is the moment of the force with respect to the point, but it's still not the moment with respect to the axis. For that, for the moment with respect to the axis, I need first of all how much is the unit vector in the axis. The unit vector in that axis is going to be basically the position vector CD. The position vector CD is in this direction, in the direction of J or Y is 8 and 6 in K, divided by, in order to convert the unit vector, the square root of 8 squared plus 6 squared, which is basically 0.8J plus 0.6K. And the last step on this problem, as you can see here, is just dot multiplying the moment, which I have, times the unit vector that I already calculated. So basically, if I want to calculate the moment of the force F with respect to the axis CD, is going to be the dot multiplication of 0.8J plus 0.6K and the force, which is negative 720J plus 240K. When we do that dot multiplication, is J times j, or dot j. Remember, this is magnitude basically, because the direction is the direction of the axis. 0.8 times 720 plus 0.6 times 240, and this value is negative 432 pounds per foot. This is the result. Now, what does this negative sign means physically regarding this value? Because I say magnitude, right? Magnitude, negative magnitude, that sounds kind of weird. But what this negative value is telling me is that I calculated with respect to the vector CD. If this is the axis, and this is the positive direction of the axis, if the result was positive, then the rotation will be happening around this axis in this way. Around this axis in this way, the rotation. Because this is negative, the rotation is coming into the axis, meaning the vector for the rotation is coming in this direction. Rotation in this direction with respect to the axis. That's what the negative sign means. And this is one way of solving the problem. Other way of solving the problem would be triple scalar product. But I'm going to use something else. I'm going to do something even more weird, if you wish. Or if you will. Not more weird because it's not weird at all. But it's something that a lot of people don't even figure it out when you do it. I'm gonna use triple scalar product. And also, I'm going to use the principle of transmissibility that we discussed previously in this problem. Why? Because the principle of transmissibility says that basically I can put this force wherever I want to along the line of action. The problem is solved. This is just another way that you could solve it. So I'm going to put the force, instead of being here, I'm going to slide the force. I'm going to put the force at this location here. This is going to be my force, F. And the unit vector of the axis, I already have it. And instead of calculating with respect to the point C, now I'm going to calculate it with respect to the point D. So my arm is going to be this. This is going to be my R for the force. And this is going to be my force. And the result has to be the same. So applying triple scalar product, the first thing that goes here is the unit vector in I, unit vector in J, unit vector in K. And then you have Rxi, Ryj, and Rck. And then you have the force Xi, force Yj, and force Zk. And you do that triple scalar product. Our unit vector we calculated before, we just need that, and our unit vector was 0.8 in J and 0.6 in K. We just calculate that here, you see, 0.8J, 0.6K, that's the unit vector. Our R from here to here is basically composed of two components. One component is going to be from here to here, and that's 6K, and the other one is from here to here, and that's -4 in J. So it's going to be 0, -4, and 6. And finally, our force is the same force anywhere. So our force we calculated before, and it was -60, 40, and 120. And then I do the triple product here, and the triple product is going to be this value, 0, that multiplies this times this minus this times this, which is 0, negative j, but j now is 0.8, that multiplies 0 times 120, 0, minus 6 times negative 60, plus k, but k is now 0.6, that multiplies 0 times this is 0, minus this times this, negative 4 times negative 60, and this result is going to be equal to negative 432 pounds per foot, which is exactly the same value that we just calculated in our previous problem, in our previous part. Once again, the negative sign is an indication of the moment with respect to the axis is rotating inwards towards the axis, not going out of the axis. What other way could you do that? Well, you can try to do calculate the moment of the force with respect to the point D, which is just basically this part, and then multiplying that by the unit vector, which is the same thing that we did before. I mean, any way that you want to, the procedure is the same. Calculate the force, the moment of the force with respect to any point. If I have a point here, I could calculate, let's say that I had the point, and I am able to calculate the coordinates of this point. And I want to, I don't know, calculate my arm from here to here in order to calculate the moment. Well, I can do it because this point belongs to the axis. Or from here to here. I can do that. This distance times the force, or this distance times the force, vector-wise. And the key after that is I have to dot multiply all the time by the unit vector of the axis, because what we're calculating basically is the projection of that force, or that moment in this case, with respect to that axis. Well, you have two more new problems. Next class or next session, I'm going to start dealing with couples, moment of couples in 2D and 3D, and distributed loading. And once we reach that point, that's going to be the material for the first exam, at least for this term. See you later, guys, and I hope that you are following these lectures. Have a nice day.